we should always start when talking about optimising a breeder's equation. So obviously we're talking about selection accuracy, which involves both heritability and also heritability within a trial, but also how well that trial describes what's happening in other years and at other sites, the correlation with other data sets. Selection intensity. One of the best ways to drive selection intensity is to get your population size up so that you can arrive ultimately with one or two lines that have come from a larger number. That's where you get your high selection intensity from. I mean, just selecting harder on data that doesn't really lend itself to more intensive selection doesn't normally result in higher rates of genetic gain. When the whole thing is divided by time, I mean, rate of genetic gain, rate is that key word there, and time taken per breeding cycle is just so critical. And when I'm talking about time with this equation, I'm talking from time of the breeder's cycle, so from cross to cross. That's what drives the rate of genetic gain. From cross to release, that equation is less important for the rate of genetic gain. It's from cross to cross, particularly when recycling parents, which is a critical step and a critical activity. And genetic variance, I find that, I think of myself when I think I misinterpreted this part of the equation for the first part of my career, where I guess I thought, I'm wanting to maximise every component of this equation. I don't think that's the case for genetic variance. You need to have the variance in the population, but quite often if you are making a really wide cross, that's a great way to get a lot of genetic variance. Unfortunately, a lot of it is on the back end, and you can find yourself creating a lot of rubbish. So let's start with parent selection, and I really wanted this presentation to come after George's presentation on product profiles, because it really starts with the product profile to understand what are the key traits that will trigger adoption, the must-haves, because understanding that then feeds into understanding what parents it is that you need to be choosing. So what are the must-haves? Often the must-haves are a disease and end-use quality. To enter into a market, you need to have a certain level of disease resistance, and the variety needs to have the quality to serve the end-use purpose that it's being grown to serve. And beyond that, then it's quite often yield, obviously, that you're trying to push the boundaries of yield. But to have a really high-yielding line that doesn't have the appropriate disease or quality often won't get grown. So then, when thinking about parent selection, does the trait exist amongst otherwise elite germplasm? And the answer is either yes or no. If the answer is no, then pre-breeding or trait breeding is required. And this comes to the question that was asked earlier in George's session. So what is pre-breeding or trait breeding? It's breeding that is focused on delivery of elite parents with novel and useful genetic variants in breeder-preferred backgrounds. There must be focus on delivering the above in the shortest time possible and delivering it to the core breeding program. Pre-breeding is not core breeding, which is focused on developing varieties and to replace the currently grown varieties, so achieving those product profiles. So I wanted to make this point because in some programs, the distinction is not clear. And when the distinction is not clear, this is a big problem, because what happens is that the core breeding program is making wild crosses or is dealing with material that is never going to, or it's going to take a very, very long time to achieve that product profile. And conversely, if the pre-breeding pipeline is trying to release varieties, that's not their role either. And then the pre-breeding may not be getting the attention that is required. So it's important to make that distinction. And in this slide, I've started calling pre-breeding PB and core breeding CB. I'm relatively new to the CGIAR, and I've learned that if I don't start using acronyms, I probably won't survive, because there are a lot of acronyms in the CGIAR. So once a clear distinction between the two is made, then resources can be allocated appropriately. And you can't do that until you make that distinction. And it's up to the individual crop as to determine where that split should be. I mean, I try to think of what a general rule of thumb could be, and I come up with between 0 and 25%. I put 0 because sometimes pre-breeding may not be required, but normally some is. You probably don't want to go higher than 25%, and there's probably good cases for why you might in some instances, but as a generalisation, you don't want to go too high because at the end of the day, the core breeding program is the one that's delivering varieties to growers, and if all of your resources are going to pre-breeding, then you're never going to get a variety into the marketplace. So I just wanted to acknowledge that getting that balance right can be a real challenge in the CGIAR because often you have funders come in and say, oh, I want to fund breeding for this trait, which fits into pre-breeding. And very quickly you can get a lot of funding for what is pre-breeding and the core breeding program is really struggling to get the funding that it needs. And so I'm just wanting to make that acknowledgement that it can be difficult and it can be something that you're going to have to try and fight against if that's what's happening in order to get that balance right, or get the balance to what you think is where it should be. I wanted to make the point that the two activities need to be separated, but particularly for a small crop breeding program, that often the two will need to be conducted sometimes by the same breeder. So even if that's the case, there's nothing stopping from a breeder saying, okay, I'm allocating 25% of the resources I've got, or whatever the percentage may be, to pre-breeding and the rest to core breeding. But it being very clear in their mind what the objectives are for the two, and that they're very different. Now, some people might say, oh, we need to ensure that we're investing for the longer term, and core breeding is for the short term and pre-breeding is for the long term. Core breeding is for the long term as well, so I just wanted to point that out. As you're recycling parents and you're empirically building upon those, that's a long-term process, and so I would argue that core breeding is also an investment in the long term. And like I said before, ultimately value provided by pre-breeding has to be realised by going through the core breeding program. Once parents are selected, then a crossing strategy needs to be set up. And it's good to set boundaries for crossing. I found in my breeding, I found it really useful to try and set clear boundaries in order to reduce the number of combinations that will have a lower likelihood of success. We all know that a lot of crosses often come to nothing, never producing a grown variety, and the reality is that with some critical thought and some clear predetermined boundaries that you may set for yourself, knowing your germplasm and knowing your targets, that it is possible to come up with a set of boundaries that are going to result in higher likelihood crosses. When I challenged myself to try and do this, the immediate reaction was, well, I'm already doing this because of course I wouldn't be making crosses that don't work. But when I really critically had a look at what I was doing, I realised that, well, some of these are actually fairly low likelihood, and I was able to really focus on getting larger population sizes out of a smaller number of crosses. So that's just one point I wanted to make. And the other is that, this crossing strategy is about trying to think about how they're combined. So, if you're talking rice or a fixed line program, if you've got one parent that is better than the other, or if you've got one parent that you're probably wanting to bring through a limited number of genes or traits, and the other parent you're wanting to maintain, then looking at a BC1, a backcross one, might be something to think about instead of a trait cross. It's just trying to include that as part of your rules, is to think of the traits that are being manipulated and the genes behind those traits. Another might be to consider the midpoint, which is the best predictor of, in a lot of cases, progeny performance. And this is to try and drive crosses that are truly elite by elite. Again, in my own crosses, sometimes I'd have a parent that I really liked for one particular reason, But if I really was critical on myself, and looked at what the midpoint is for every trait that exists in a product profile, and I just want to show up I'll bring up an example product profile that I used to use for my program. This is, let's get this out of the way, so I don't have a lot of room here. So here's an example product profile. If I really mapped out for every one of these traits that exists in column D, if I calculated what the midpoint is for any particular cross, this is one way that I used to use to try and help me to put a red line through a large number of crosses, because suddenly I'd realise that for a particular trait, if I needed to, I'm just going to move that, if I needed to maintain all of these traits, and it might be 2 or 3 of them, the midpoint might be so low that the chance of maintaining at a certain level was so low that I realised that it wouldn't work, even though for some of these other traits it might have been a fantastic cross. It needed to achieve all of those things there. So that's something that helped me in what I was doing. So like I said, it helps to get to an elite by elite situation. Another one might be relying on transgressive segregation, trying to get better than both the parents in a number of traits, is something that is really difficult to do. I mean, often you're having to do this for 1 or sometimes 2 traits, because that's what the breeding is for, is to push the boundaries of yield or whatever your main trait is you're trying to push. But if you're trying to get transgressive segregation for 3, 4, 5 traits, then if you look at your normal distribution and you try and take the tail for every single trait, then the required population sizes blow out very, very quickly. Okay, so like I said, it's good to set clear boundaries, which could be your own crossing rules, which will result in less crosses. Now, less crosses is good because it'll give you higher population sizes. And thinking about this, I mean, required population sizes are often underestimated. I know that in my breeding, I used to underestimate the required population size. If you've got 4 traits, and you mentioned earlier that you often can't handle more than probably up to a maximum of 3 traits. So, I mean, in this example, I'm getting a little ambitious with 4 traits, and even if they're controlled by as few as only 3 genes each, the required population size is over 4,000. That's pretty high. And if they're controlled by 4 genes each, you're up to very quickly up to 65,000. So it gets out of hand very, very quickly. I don't know why this point is here again. I apologise. So crossing discipline, adhering to your own rules. So just to try and summarise what they might be, only using parents of a certain elite performance. So if you're going to calculate the midpoint for every one of those traits, set a boundary for if it falls below on a particular trait, below a certain level of midpoint performance, then perhaps that combination isn't good, or perhaps one of those parents shouldn't be included. Another really useful strategy is to explain your crosses to a colleague and have it critiqued. This is something that in the private sector happens a lot, in the public sector, and I mean the problem is CGI breeders are so busy quite often. I mean, you're doing so many other things that you're being asked to do so many things that a private sector breeder isn't asked to do. I mean, sometimes you might come back from a training, you might have come back from a week of training, being overseas, and you arrive back in the office and the crossing block needed to be done by yesterday, and it just needs to be sorted out and put through to your team to be implemented. So I understand this is something that can really take discipline to have it done in time to get it critiqued, but it can be really useful. I mean, even going through the process of explaining to somebody, I'm making this cross and these are the reasons for doing it. I know for myself, when it comes to George's point, that if someone's not looking over me, then sometimes I can sort of let a few things slide in. And that's for me personally. And when you're explaining something that you yourself probably know might not be 100% or as good as some of the other crosses, you'll know as soon as you're trying to explain it that feels a little bit uncomfortable. And having it critiqued, I mean, even if you do still feel comfortable with it, having it critiqued by a colleague, you don't have to listen to everything they say, but it's useful. I mean, two minds are always better than one. And say, well, why do you think this one's going to work? And again, it gives you an opportunity to put a red line through a few of your crosses and hopefully get larger population sizes.
Yeah, this is extremely useful, and it's basic, but it's really, really, really important. So thank you very much. One question I have is, like, when you're doing genomic selection, it sort of erases a lot of this. You end up with your genomic estimated reading values, and you cross among these predictions and stuff like that. So you don't pay as much attention to the individual parents as thinking of it as an elite by elite cross. So how do you sort of factor that into this kind of a system?
That's a great question, and to your point that a lot of this is basic. I agree with you. And the other thing I wanted to point out, which I didn't at the start, is that sometimes, for myself personally, sometimes I like being told stuff I already know, because sometimes it gives me a kick up the pants to actually do what I know I need to be doing. But your question about genomic selection is a really good one. For me personally, my experience with, my experience with genomic selection, like most breeders, is fairly limited because it hasn't been around for 10 years. And I personally am not very comfortable with that way of utilisation of genomic selection. I think genomic selection is a brilliant tool for getting rid of some of the lower end of the population. I don't have a lot of confidence at this point in using it to pick the highly elite lines which I would be looking to allow into my crossing block. That's me personally, but you're right. I mean, if that is the approach and that's the strategy that's being adopted, then I would suggest making a very large number of crosses, and in time, maybe within the next year or two, when there is some more phenotypic data on those parents, reviewing those crosses and being willing to actually put a line through a large number of those combinations if you're in a clonally propagated crop, or if you're developing populations, then before fixed lines are derived, put a line through them and be willing to revisit on a regular basis those. I think that's a good approach anyway, to make a larger number of crosses and go through that process. Another way that I would do it is, rather than, if it's going to be used quite aggressively like that, and I call that quite aggressive, I would prefer to instead make a complex cross, like a three-way cross, even if it's a BC1 or a top cross, and actually use the genomic selection on the F1s for well-characterized, still using very well-characterized parents with good phenotypic data, and then use it on that. And then that's another way of using it quite aggressively. And effectively, I mean, what F1s you allow to, complex F1s you allow to contribute to the next generation is like a parent. And so in a sense, you're using the prediction to choose your parent in that way. I prefer that way of using genomic selection because I at least know that all of the genetics being contributed by the parents, I've got a pretty good idea as to what they're contributing. But that's a great question, and this is something which I'm not going into too much in this presentation, but the strategic application of tools like genomic selection is at the heart of what Module 2 is here to try and assist with, because there are some really complicated questions like, how do you apply these things? How aggressively should we be applying them? My personal approach is that I'm comfortable applying them as aggressively as what the data tells me that it's able to choose, in this case, the parents, and how accurate it is. Again, I think genomic selection, in my mind, it's by far and away accurate enough to use for selections, but not necessarily for parental choice without phenotypic data. Another question over here.
I think one of the essence of using genomic selection is to reduce the time. And then when you go into what you suggested, maybe test cross, doing those crosses and what have you, you are also increasing the time which we want to reduce. For instance, something like cassava, we are thinking of because the breeding pipeline can take you 8 years to come up with a new variety. But with genomic selection, you can, jumpstart and go into another, or fast track and go into 5 years or 4 years, as case may be. So I don't know.
That's a great point. You're right. The way genomic selection, I think genomic selection can have impact on most parts of the breeder's equation, but one of the main parts is to reduce the breeding cycle. And so if you're not using it to select parents earlier, then you're not achieving that. I may have done a poor job of explaining what this is, again, this part is my personal view, but I think it's nice to have the conversation and talk between breeders across crops about these things, because we don't always get an opportunity to, and in the CGIR we've got that opportunity. In the private sector they don't talk between each other very often, so I think genomic selection is a great way to help choosing parents earlier, and I just don't think, I personally am just not comfortable choosing on only genomic data. So in a more traditional program, let's say you develop your products, whether it's a hybrid or a cleanly propagated line or a fixed line, you might go to 2 sites by 2 replications or 3 replications, and the following year you go to a large number of sites. You're all familiar with the process. I think genomic selection offers an opportunity to shortcut that process. So first of all, like I said, if you're able to knock out the bottom, whatever percentage you think is appropriate given the accuracy of the prediction, the bottom 10%, 20, 50, 60% of the population, suddenly you've got a smaller number of lines, or even if you arrive at the same number of lines, they're a more elite set of lines because your rubbish has been knocked out. Then you can actually, you can go to a more aggressive testing strategy if you've got the genomic data. So instead of going to 2 or 3 environments, you can reduce your replication. If you've got the genomics data, you can put that data into the model, into the analysis, and you're likely to get a better prediction and better quality data than if you had a higher amount of replication without the genomics data supporting it. And if you want to get even more aggressive, there's some really good models available where you can actually you can use those additional plots that you save through replication to spread to more environments. So instead of going to 2 or 3 environments, if you have a third of the replication, you can triple the amount of environments you have. And if you even want to get more aggressive, you can test more sparsely. You don't necessarily have to have every line at every environment. So you could test at 6 out of 20 environments and use the genomics data to help predict for those other ones. Now suddenly in this example, we've gone from 2 or 3 sites to getting good predictions for 20. And so I think you can start to see that, well, suddenly I'm going to be more confident in choosing my next parent at a much earlier stage than what I was before. And even if you don't choose a parent from that stage where you've got now pretty good phenotypic data, it's still only from 1 year and we're all aware of the year effect, if you've got better quality data, you'll drive down your numbers faster with higher selection intensity because you've got the confidence in the data. And so the next year, you can test even more thoroughly than what you would in the second year of testing. And so no matter what way you look at it, if you go down this road, you're going to have confidence in that parent much sooner than if you didn't have the genomics data. So that's my own view on it. So I think that you can really use genomic selection to reduce the breeding cycle and choose your next parent much earlier. I personally am just not comfortable choosing without some phenotypic data as well. That's a really good point.
Michael, this is Ismail. So this is an important question because for us, we've aggressively used genomic selection to do like an annual or every 2-year recombination cycle. In one way, we have gone very fast, and everything that we have genotyped, we have also done phenotyping, so that has increased our training population sizes, and now we can look back and see which of those parents selected for genomic selection are actually validated based on phenotypic data. In the context of this excellence in breeding, genomic selection, the use of molecular markers are all strong components. But it seems like as a group, we are still on shaky ground as to how and when to use it and so on. So there's room, I think, for the entire community to really dig deeper and come up with a set of recommendations that breeders can use instead of everybody going home and learning from their own mistakes.
Yeah, that's a great point. And Excellence in Breeding will be putting up, I mean, you could call them recommendations or you can call them things to consider. And we'll be putting that up in the toolbox in this space in the near future. But you're right. I mean, trying to work out, I don't think the question is whether genomic selection will work or not. I'm pretty confident genomic selection absolutely will add value. The question is how aggressively to use it. How much confidence do we put in the data? And that's not a question that you can just give a general answer to, because it's going to be different in every crop. It's going to be different depending on how many lines have contributed to the training population. It's going to depend on what the relationship is between the training population and the test population. So it's going to be different for every population you look at. It's going to be different. But the key is that you have that data. You've got the data in front of you. When you develop that training population, you can test the relationship between the training pop and the test pop. You can remove lines from the training population to see how well the prediction can predict. You can artificially remove lines from the analysis to see how well it can predict. And this gives you an idea of the accuracy. And if it's a similar level of accuracy to what a single year of yield trials might give you, then you'd have to ask yourself, would I pick a parent from a single year of yield trials? Maybe not, depending on how many sites it's across. And I mean, so I think this is something that you're right. We probably need to. I think it's about asking the right questions, and we can, in Excellence in Breeding, we can help by start to pose what some of those questions are. What are the questions you should be asking yourself to ultimately answer the bigger question of how aggressively do I use this tool? It's really important, and I think my personal thoughts on this, and this, again, I'm getting into my opinion, is that I would be more comfortable using it in a more conservative way until we get more experience with how accurately these predictions can predict, but still use it. I think that the risk is that that genomic selection is being talked about like some sort of silver bullet. I think it's just an extremely useful tool. I think if the expectations are too high on it and it doesn't deliver, then the risk is that breeders will say, this doesn't work, I'm not using it anymore, it's stuffed up my program for the last 2 years, I've not made any gains when I I could have made gains the old way. I think we integrate this with what I call the old way. We know what's working, let's add to it. And we can add to it in a fairly aggressive way, but let's take steps that we're pretty confident are going to work based on what the data itself is telling us. Yeah?
Actually, that was not my question, that was a comment. This is my question now. On the crosses, because we do crosses and sometimes we find out that after field proofing the parents that you used, the progenies, and you realize, this and this genotypes are good parents, their progenies perform far better than average. So the question is, should we take advantage of that information and continue to recycle and reuse those parents versus use the progenies from that parent in order to continue driving genetic gain forward? So for our clonal propagated crops, the crosses that we do is not maybe like the seed crops and other crops. We want to learn from the seed crops like maize and so on. how does that work? Is there a parent that are used more often than average, or is it that every generation, every few generations, the parents are replaced?
That's a great question. I hope I've understood the question properly. I think it's fine to use a parent more than others if it's a really elite line. When it comes to whether or not to use or for how long to use that parent, I think that if you're having a really critical look at what the performance of that parent is relative to the other options, if it still stacks up, then it's good to keep using it. And normally, I mean, in the private sector, a parent is often used for a number of years. It is very rarely used for longer than when its progeny start coming up to a point where there's sufficient data on its own progeny, because unless the cross that was made was too wide, generally there should be progeny which are better than that elite parent. And if there's not, then something's gone wrong, usually, with either the cross was too wide and so it brought the progeny back too far, or there was something that went wrong in the selection process. But George, did you have something to say? No. So I mean, that's what, I can tell you what normally happens in other breeding programs I'm familiar with. But if it's as long as it stacks up, it should be good. And I guess back to the point of the crossing strategy, and this is less pertinent to the clonally propagated crops, but I always find it useful to make some BC1s, backcross ones, with a highly elite line, because if I do that, it's almost my insurance policy. I know that if I make a BC1, I'm extremely likely to get something that on every trait is going to at least match that parent, and I could fairly easily find a few traits where it's better. So it's a little bit more conservative. You're probably not going to bust through with an absolute gangbuster, but you've got some other crosses for that as well. But you have an insurance policy there where you know that from that crossing block you're going to have something that is better. And this comes to the point that if I've got progeny at a BC1, I'm always a little bit more confident to choose a parent out of that progeny, because I know the underlying I know a little bit more about the underlying genetics. There's always, when you're phenotyping, there's always a lot of G by E, and there's always a component of unknown. If the more I know about the underlying genetics and the structure of it, when I say structure, then I've actually manipulated that structure through the crossing, then I can have a little bit more confidence about what that unknown component is likely to do. And again, it's a little bit, my understanding is it's probably difficult to take that approach with a clonally propagated crop. I need to have a bit more experience with that.
Thank you, Michael. I was thinking, I've had a lot of discussions with other breeders on IITA campus. There are two things. Looking at parents that are really good based on the per se performance of the offspring or the progenies, and you have a good parent with good combining ability for the trait you want, you could continue using it. But for us doing clonally propagated crops, you could also, you said elite by elite, if some offspring or progenies are doing better than the progenitors, such that, whether it's by heterosis or whatever, you could also pick those ones. But then we also check by looking at the pedigree. What are you going to cross that one with? Is it going to be something by inbreeding, crossing siblings, or what? So all these things guide us to know whether you continue using the parents or the progenies. But then the truth is that the performance of the parents is known by the performance of the progenies that you get from it. And then you could also decide to select from the progenies, those top performing ones, and then cross them to another, but not with them. So these are things here. Because once you fix a trait for a clonally propagated material and it's good, They are there. Unlike seed, maize, and other, so their own will be different.
I agree with everything you said, and yeah, great comments, Betsy. I don't think anything else really needs to address there. That's some good points. Right, so I was on getting a colleague to critique the crosses. Another thing that could be done is to, at the time of cross, and I call this crossing discipline because I think most people would agree these things are a good idea, but a lot of us just don't do it, and I'm guilty of that in my own program because you're just so busy, and I mean to do it, and I mean to get back to it, and I know why I make it. I know why I make a cross, but the reality is that in 2 years' time, I often forget some of the details, and so if you can record at the time of crossing why the cross was made and the weaknesses to watch for, this can really help with selections later on. I mean, I've done it sometimes, and I've looked back and thought, this is so helpful to me later on. I've gone other times I've meant to do it and not done it. And to be honest, I probably don't know what I'm missing out on, except for when I do it, I know how helpful it is to me. List all known segregating and fixed genes. It's just an extra step to go through. I mean, sometimes this is a process where you might be trying to push the boundaries or needing to hit a certain level for a particular trait, and you go through and you might realise this population isn't even segregating for the trait that I'm trying to push the boundaries on. All the progeny are going to be fixed, so you can put a line through it. But it's going through the process and asking yourself the critical questions that can highlight some of these fairly basic things. And lastly, make crosses for a specific product profile. So when George gets into some real details as to what product profiles look like, I expect that there'll be a profile for a particular market class. Now, whether that's a geographical region, or even within a geographical region, there might be different product profiles for different market classes that respond to different end uses, perhaps, or different quality types. If you're making crosses for a specific product profile, you can be really targeted, and you can really identify what are the best parents for that particular product profile. Because sometimes there are very broadly adapted parents, and they can be really good to use. I'm not saying don't use them, but if you're making the best combination for a product profile, then that's the best way to achieve that product profile. And sometimes it might be that particular parents are useful across a number of product profiles, because you will probably have a number of them as you're breeding for different geographical regions or market classes, or even combinations of the two. And so if you're using even the same combination which is appropriate across different product profiles, that's fantastic. Do it for each, because it's probably a pretty good cross. And so if you have a larger population size for that cross, that can only be a good thing. You're giving a good combination a better chance of success. So once a robust strategy is in place, this is simply recycle. I mean, this is about building on the gains of the past. Recycling is the only way to make consistent gains. Otherwise, you're relying on making increasing gains from similar crosses, which is just not sustainable. So it's called different things in different crops, but what I'm talking about recycling is you make a cross and you develop progeny, and finding the best progeny as quickly as possible to use it now as the new parent, and then continue to go. Given the points that were made earlier about understanding how to interpret that data. And the breeding focus must be on identifying that next round of elite parents as quickly as possible to drive that breeding cycle. So once you're thinking about, once you've crossed off your parent selection and your crossing strategy, then you're looking at line development. So what is the line development strategy? So, I mean, it could be, if you're talking about a fixed line, I'm talking about going through the segregating phases. If I'm talking about a hybrid crop, what is the strategy of developing going through the segregating phases to get ultimately to your parent? And if you're talking about a cleanly propagated crop, what's your strategy for going from cross to getting material which you can take to the field? There's a number of steps that you have to go through. How fast are you trying to do that? what approaches are you using? There are different approaches. Some are faster than others. Some will give you a larger strike rate in terms of progeny. So thinking about that strategy because often breeders in this space are faced with one fairly big trade-off. They can either go fast, and if they go fast, then it's either costly to them, and so they can't generate the same population size, or they can't impose the same level of selection pressure along the way. Particularly in a fixed line program, you might have segregating phases. You might be able to select on a single plant basis. So that's the trade-off that breeders are often faced with. And so I just wanted to talk through how that trade-off plays out. So obviously from the breeder's equation, which I've got there again, speed is very important. So if we can get 2 to 3 generations per year, then that's 2 is probably a minimum. 3 is pretty good. For cleanly propagated crops, moving to testing and parent selection as fast as possible, given the biological constraints in terms of how that is done. So, like I said, speed can present a trade-off with selection pressure. So let's just have a look at how that plays out. If you can reduce your crossing cycle from, this is fairly aggressive, from 8 years to 2, and 2 years, this is moving through to the testing phase pretty quick, and you might only have 1 year of field data, but you might have to have genomic data supporting it if you wanted to select a parent that quick. But this example is hypothetical to show the point. If you can reduce your breeding cycle from 8 years to 2, and your genetic gain per cycle is reduced by less than a quarter, then you're in front. So it takes the pressure off the level of performance of that next parent and still being in front. So slower strategies allow larger numbers to be tested. But let's look at it in a different way. Let's look at the impact of that. So high numbers are definitely important in breeding. We all know this. We know that breeding is a numbers game. But let's look at how important it is. So if you've got a population size of 256, just from very basic quantitative genetic theory, you can manipulate 8 genes in that situation. So if you increase that population size from 256 all the way up to over 1,000, you can now manipulate 10 genes. It's actually not a big increase in the amount of genes that you can put together into a single line between those 2 parents. So you'll require 4 times the resources to go from 256 population size to over 1,000 in order to manipulate just 25% more genes. So I put the question there, is that a good deal? Well, we know that breeding is a numbers game, so you'd always take 1,000 over 256. But would you take it if you had to take longer to do it? I personally wouldn't. I don't think that the trade-off is there. So high numbers are very important, but really, when you do the comparison, speed almost always wins out to go faster. Now, this assumes adequate recycling of the germplasm, which is a must. Because if you're not going faster to find that next parent, then what's the point of going fast? So, still looking at speed versus selection pressure, if crossing can become more targeted, like I suggested earlier in the presentation, then this can help to drive up your population sizes within the populations that are left. So, hopefully, you can have your cake and eat it too. That's where we want to arrive at. So, hopefully, you've still got sufficient population size to manipulate the genes you're needing to, but you're doing it as fast as possible. But back to that analogy of that we had earlier of speed versus population size. There was I thought I had it here somewhere, sorry. No, that's right. I'll leave that point, it's not there. Okay, so once you've gone through your line development stage, you're up to product testing. So the objective is to identify the next highly elite parent as quickly as possible so you can recycle it. And to identify products that best achieve product profile, that that can beat what was currently growing, so you can get it out into the market. And we all know this, I just wanted to bring it to the front of mind. So the next thing to consider is, okay, what traits do I test, and in what order do I test them? So you must prioritise testing of the key traits in the product profile, particularly those that are most likely to be a problem for that particular population. I mean, some of those, in that example product profile I had before, some of those traits you can be fairly confident your progeny are going to tick the box. Others, you're not so sure. These need to be tested. And testing anything else that's not in that product profile, you have to really ask yourself why you're doing it. So, even if they're maintenance traits, so even if you're not necessarily trying to push the boundaries like you might for yield, if you're talking disease and quality, they're really important to test for. And to answer this question, what are the considerations? We're looking at you need to understand what is the heritability, both within and across trials. What is the cost of testing each of these? And what is their response to selection? So when I say response to selection, I'm saying when you test these a given population, are you likely to cull 10% or are you likely to cull 90%? Because that starts to factor in on which one to test first. And when do you test? Do you test in season or out of season? Often there's opportunity to test for quality traits out of season. And if that means you can do it earlier and get your numbers down, then prioritising this can be a really good thing. So, I mean, once you have this information, you can start to target earlier the traits that have higher heritability. You can start to test earlier those that are the traits that are cheaper, because for a limited investment, you can get your numbers down to better test a smaller number of lines. And your response to selection, again, testing earlier those traits that you can knock out a larger number of progeny. So what else needs to be considered when it comes to product testing? It's about resource allocation. Often you have a set amount of resources, and like I said earlier this morning, if you look at all the decisions that you could possibly make, there are so many different combinations of ways in which you could do this. And there are a number of right ways, and there are probably a number of wrong ways. And you're probably doing none of the wrong ways. But it's good to ask ourselves these questions around what amount of replication is required, both in the field and the laboratory. And I put laboratory there because sometimes replication in the lab gets forgotten. I don't know why. Sometimes it's more expensive testing, but you need to understand the quality of the data, because that helps to determine how intensively you can select on that data. Otherwise, you're kind of flying blind. But also in the field, number of locations. Generally, it's always better to reduce replication to pay for more locations. There's always so much noise in a phenotypic data point, and the sources of those noise are generally spatial variance or in-trial variance of some sort, and G by E. And if you can go across a larger number of environments, then to some extent, that data point serves as an extra replication, as well as helping you to understand what the G by E is. So it's generally always better to go to more locations.
I have an issue with heritability, because I'm aware that when you increase your replication, you are likely to have a better heritability. So what we are suggesting that we should reduce heritability and increase the location. So how does
that's a good point. You will reduce the heritability within your trial if you have less replication. But you have to ask yourself, what is the relevance and the representativeness of that data? So if you think of the target population of environments that constitute the environments that product profile is for, and then if you take any individual trial and you ask yourself, for that trial, what is the correlation between the results here and the results in that target population environment? due to G by E, it's normally very small for an individual trial. And then you could have extremely high, let's say the correlation is 0.2, because there's a year effect and there's also location effect. You put them two together, if you're getting 0.2, you're probably doing, that's a fairly reasonable sort of number. That's what normally comes out. It's rarely above 0.5. So if you're getting a heritability of 0.8 and the correlation of 0.2, the relevance of that data is 0.16. If you instead had the opportunity to go from 3 replications to 1 with a grid check, so you can do a spatial analysis still, and go to 3 sites instead of 1, then suddenly that correlation is likely to jump from 0.2 to maybe, I don't know, 0.5. It's still probably not great because of the year effect, but okay, it's a lot better than 0.2. But your within trial heritability, it might go from 0.8 to 0.5. So now you're faced with 0.5 by, what did I say the correlation was? 0.5 as well. Now you've got a relevance of 0.25, which is a lot better than 0.16. And that's the way it almost always plays out, that your reduction in heritability is almost always smaller than your increase in relevance. And it does depend. It depends on, well, you might argue it depends on how much G by E there is, but if there's not a lot of G by E, then those three sites are going to be fairly similar to one another. And if you do an analysis that can borrow strength from the different trials, I'm talking about a factor analytic type analysis, then effectively you've still got 3 replications. And if you're doing that sort of analysis, it's almost impossible for more sites to not be a better situation than more replications. But it's a good point, and it's one that does come up often. Any questions? Oh, yeah, up here.
Yeah, thank you for that point. Sometimes the challenge, I'm Babukar Mane, by the way, working for Africa Rice. I'm the irrigated lowland rice breeder. Sometimes the challenge is that in your design for these trials, you are thinking also about the varietal release regulation. So sometimes the national release regulations are asking for 3 replications. So if you want to go down to try to reduce the number of replications and have more sites, that data, the release committees, many times will not be accepting it. So sometimes that's the dilemma our national partners are facing.
That's a really good point. And normally if you're talking about at that stage of the testing pipeline, you're talking about a smaller number of lines, and to be quite honest, if you by that point you're already in the maximum number of locations that are available to you, and if you have 3 replications instead of 1, you're not talking about a big difference in resources because you're talking about a fairly small number of lines. And even if all of that weren't the case, you're right, you have to conform to the national system. You're absolutely right. What I'm really talking about here is particularly in early generation trials, your first and second year of yield testing, because that's when your numbers are so large that making a different decision here can make a really big impact. You quite often have a very small number of locations, so expanding that out just a little bit can have a huge impact on the accuracy of your data. And reducing your replication can have a huge impact on the amount of resources that makes available. But yeah, you're absolutely right. Any more questions on this? So this replication versus...
Michael, so there's another way we can think about it by partially replicating the trials within locations. Then that can generate some data to estimate within location heritabilities. and interconnects that with the other locations also.
That's a really good point. That's and this is taking it to the next level where, so what Ishmael was talking about was, I think what you're talking about is really sparse testing. Yeah, so if going to not having necessarily every genotype in every site. So in my example, I said go from one site, reduce your replications, and go to 3 sites. What Ishmael was talking about is, well, why don't you go to 3 out of 12 sites? Every genotype goes to 3 out of 12 sites. So to explain that a different way, any particular genotype is still at only 3 sites, but they're not at the same 3. So you don't have a complete set in any one environment. And if you can do this, or when you do this, and I've done this in breeding programs I've managed, and it's really powerful, what you can do is you can look at the correlation between sites to predict for those genotypes that aren't present. And the predictive ability becomes even more powerful if you've got genomic data supporting it. But no, that's a fantastic point, and can really drive up your data quality. Yes, up back.
Even at early stage, when we have a large amount of genotypes or materials, we can still use even augmented design with no replication at all. And we can maximize on the location, but with no replication, because you have maybe 1,000 with check, with check. And then you use augmented. And at the last stage of evaluation, like the terminal stage, you need both replication and location. The replication has to be there, at least 3.
Pardon? Yeah, I think the question, is more of a statement that as you get to your later stages of testing, you need both replication and locations. And I totally agree. Again, I'm talking about the early stages of selection. As you get to your later stages of selection, if the process has worked, you've actually got less genetic variance between the lines or the products that you're testing. And so you do need both. You need locations and replications. But again, hopefully your number of lines is low enough that you can afford to do this. I'm really talking about the early stages of selection. So
I wanted to say, all the points people are saying are very valid, but one of the challenges I have, my experience, that the fields in Africa are so variable that replication, one replication, normally don't get good data. So if you do use augmented designs, you won't really get good data, because the fields are so variable, they're different from the USA and so on. But the fields in Africa are very variable. You rarely find very good fields for you to do trials.
Yeah, we have this problem in Australia as well, and it's a good point that, I'm talking conceptually. At the end of the day, to use statistical analysis jargon, you need the trial to converge. You need to be able to do a spatial analysis, and you need enough replication to do that. Generally, though, if it's really that bad, sometimes even 2 or 3 replications still. The trial still may not converge if the trial is that bad. But it's a good point. You do need the analysis to converge, even if you're doing a factor analytic analysis where you're borrowing strength off the other sites. You do still need to. You need to have a stronger genetic signal than spatial variance. But I'll keep moving, because otherwise George isn't going to get to talk about genetic gains assessment. Okay, all right. He gave me the green light to keep going. Okay, so now I want to talk about statistical design and analyses. And I didn't want to get too much into sparse testing and factor analytic design analyses, because I am aware it can be done with Excel, and there's no problems there. And I'm just aware that I'm not sure how many of the breeding management systems currently support this sort of testing. Yeah, it can be done in Excel even if it doesn't. But BMS may, which a lot of you are probably using BMS. So, getting statistical design and analysis right, which is basically what I've been talking about for the last 5 minutes, can have a huge impact on the program. And in Australia, I've worked for different companies, and I've worked in both the public and private sector, and I added it up the other day and come to 17 breeding programs that I was exposed to. I wasn't actually running them all. I mean, I'd run some of them, but in some of these companies we may have 5 different breeding programs, and me and my colleagues were always very closely connected with one another and what we were doing. So we had a good idea of what was working for one another and what wasn't. So across these 17 programs, this is probably one of the biggest impacts. I mean, some of these programs had genomic selection, some did not. And this is how you use genomic selection is actually tied in with the statistical design and analysis. But one company, Monsanto, was one of our shareholders. We had the seed chipper, and the others did not. Just about every tool you can think of. Some used double haploids and some did not. I mean, when it comes to tools that they were using, there was just about every combination. And yet that was not the defining factor. It was the defining factor between those that were successful and those that were not was mostly around the crosses that they were making, how disciplined they were and how much effort and time they put into identifying what the best parents were and the best cross combinations. That was one thing. And then having a strategy which was appropriate and a really good strategy. Some of the things I'm talking about here, which you all in the room know. It's just about putting it all together. And thirdly, statistical design and analyses. This is an area that has driven genetic gain massively because it's enabled us for a given dollar of expenditure to get so much better data, high quality data, and it costs almost nothing to have a better design and analysis. So it can have a huge impact. So, I mean, we know this. If you can get higher data quality, you've got higher selection accuracy. You're driving your breeder's equation. If you've got less resources, so if you're able to get better data quality from less resources, you can put those resources into higher population sizes, which in turn allows you to have a higher selection intensity. How many? Okay. So the sort of thing I'm talking about is for a single site analysis, I think it's fairly fair to make a blanket recommendation of a Renal autoregressive analysis. That's a fairly good way of doing it. And to use BLUPs, not BLUs. For those that may not be familiar, a BLUP is a best linear unbiased prediction and a BLU is a best linear unbiased estimate. They're the same thing, except for a BLUP, the one that I'm recommending, shrinks the differences between genotypes relative to the heritability. So if you've got a heritability of 1, these two are the same. If you've got a heritability of 0.2, then what was a fairly large difference between your best and worst line is now shrunk back closer to the mean, because it's acknowledging that a lot of that variance that you see is actually, if you've got low heritability, it's actually just noise in the data. And so you do not want to be making selection on noise. And so BLUPs are a good thing. Shrinkage of the data according to the quality of the data is a really good thing for making selections, because otherwise you may overinterpret the difference between one line and another and make a promotion based on that, or a cull decision. And also, if you're looking at... Sorry.
I have a little bit of a comment of that point that you just made. I think shrinkage is good to a point. It depends on the distribution of your traits. And so if there's enough distribution, that's fine. But if you have very little distribution, so much that there's an inability to detect genetic variation, then you might want to go to raw data. Just something to consider. In general, I agree with you, but there is a caveat.
Yeah.
Which is fine.
No, I agree with you. I don't like to say it, but yeah, the breeder in me agrees in you. The statistician in me says absolutely no. But no, I mean, you're right. If you're really struggling to find something to select on, then that can be the case, but you have to be aware that you're still mostly, sometimes you just have to get your numbers down, but it still is mostly noise in that case. If your heritability is that low, then going to the raw data is, it's another way of looking at a limited amount of data so you can get your numbers down. I agree, and I've done that. But you're almost making random selections still. It's a lot of noise. But yeah. I'd like to scratch that from the conversation because it's a rare situation. Thanks, Stella. I think blue, but back to advising blups over blues, it's particularly useful if you're making selections across a number of sites where some sites have better heritability than others. If you're actually weighting your data according to the quality of the data, then you're making your selections, again, you're weighting it if you're using blups in a very data-driven way. If you're using blues and you just assign the same value to one side as another, then you're giving more value to data that has less quality than another site, and that just doesn't make sense. And just on a point, when it comes to looking across trials, I've seen some instances, not in the CGIR, I've not been this close to the data, but some instances where breeders have decided that they need to select across a number of traits, which is absolutely true, and then they'll get all of their sites and they'll just get an average across them. And some of these sites will be totally uncorrelated with one another. And what ends up happening is everything looks kind of medium. And yes, some of the lines that are very broadly adapted rise to the top, that's true, but it does dilute your signal. And if you can, even if you're not doing a factor analytic analysis, which actually models the G by E and uses that information as part of the analysis, even if you're just doing individual single site analyses, if you just do a correlation matrix to look at which sites are more and less correlated with another, and you can create a dendrogram from that, or you can even just look at the correlations and sort of draw one out yourself. If you create mega environments or clusters of environments that are more correlated to one another, and then select within each of those, often these cluster environments will sometimes be loosely attached to a product profile as well, so it can help you drive your selections in that sense. That's a more robust way of putting that data together. The last point here, multi-environment analysis, recommendation is a factor analytic analysis, but I've always used AS-REML for these analyses. For those of you that have had less exposure to statistics, perhaps a biometrician can be involved. The problem here is that, well, not a problem, there's something to be aware of, is that a lot of these analyses, my understanding is that you probably need AS-REML. That's what I've always used. I think it's worth biting the bullet and getting a license for AS-REML in order to be able to do this, because the impact is that big. Yeah. For data, I hadn't finished deleting the second point, I'm sorry. For data that is from any given location, how relevant is the data to the product profile the selections are being made for? This is just bringing it back to the product profile. So if you might have a number of product profiles, and you might have a particular disease which you're just going through your selections of stage 1s or stage 2s and just knocking out all the ones that are really bad. But it's useful to think, well, hang on, of this material that I've got, which lines are actually targeting a particular product profile, because that disease may not be a part of that product profile. And so you don't need to select for every single thing that's on every one of your product profiles. Think about, for a given set of selections, what is it targeting? Okay, so in Excellence in Breeding, we've developed some templates for understanding what your current scheme actually is, because this is something that we want to achieve as a result of this week, is to get a better understanding of, for the breeding programs that you're a part of, how many crosses are you making? How many replications are you using? How many sites are you selecting in? What population sizes are you dealing with? These are the sorts of things which in excellence in breeding we want to understand, because that's the first point to start to have the conversation with you in terms of trying to, I said this morning, we want to identify an improvement plan with you. Now, it may be that there's not one thing that you say, oh, this is something I want to improve. It may just be, this is something I want to have a look at and just explore some options. And that's the first step in that conversation. So I'll bring it up in a minute just to show what it is, and then over the next 2 days we're going to split up with groups of you. We're going to split up the rice people, the maize people, the RTB people, and the grain legumes and dryland cereals. We'll split off into those 4 groups, and we'll have individual sessions. George is going to do the same for his, and going to take a deep dive on some of the issues he's talking about, and we'll do the same for optimisation, take a bit of a deep dive, understand what your current situation is. And the other reason for doing this is that in my experience, in the later part of, or the last 8 years I've been working in the private sector, I've always wondered what my competition were doing, just because I'm interested in this stuff, just to know how are they structuring their pipeline, what's their strategy, what have they valued of that breeder's equation, what components have they valued over other parts, and you just can't get that information. In the CGIAR, we're in a really unique position to be able to learn from one another, and just to have the stimulating conversation of what our colleagues are actually, how they're making these decisions. So to not take that opportunity would be sad. And so this is a great opportunity to bring it up and to put it on and to put it up on the toolbox. We can put it on a member-only site so that it's not. You can choose to have it freely available if you wish, but if you want to have it just available to the other members, and we can do that also. We won't put it up for everybody, certainly without your permission. And we can put it up there so that we can start to have this conversation as a community and say, oh look, I see in their program that they're doing something really, really, really quite interesting, which I would like to try. I'd like to talk to that breeder about how that's working for them. So the first step to being able to do that is to document what the current strategies are. And it'll serve as a snapshot to look back on, to show improvements to funders. We're wanting to do this for the breeding strategy, and I'll show you the templates we've got in mind at the moment. And these templates are a work in progress. So I'm happy for feedback. I'm happy for you to say, look, let's make this a better template for this reason or another. But we're wanting to do it for the strategy. We're also wanting to do it for Module 3 to understand what the use of markers are. And this is a good example where I say, to show improvements, where we can say, okay, in 2018, we're using these 3 markers, and there are 100 other markers available, but they weren't providing value. And we all know, how many QTL have been published? Probably tens of thousands. How many are actually useful? Very few. How many are actually being implemented? Very few. And so there's some work to be done there to get markers that are actually providing value. And so hopefully we can say, in 2018 we were using these 2 markers, but in 2022, now we're not using 2 anymore, now we're using 8. And we're able to improve our effective population size, and through some of the other things we're trying to do in Module 2, which looks at the strategic implementation of these tools, we're able to, for example, increase our effective population size so that everything that hits first stage of yield testing, or even hits F3, let's say, has these traits, and now we can focus on the polygenic type traits like yield or end-use quality. So I'll just quickly bring up what I'm talking about here. Just make some room for myself. So for my breeding scheme, and I apologise, I don't think this template is great at the moment. I was hoping to come up with a better one, but I think it's functional. Trying to capture informations like and you can generalise here. Sometimes there's going to be changes from year to year, but generally, how many parents are you using? What are the number of finished crosses each year, or combinations that are being made? I could probably And then for what's the average number? Now this is assuming, this part here is assuming a fixed line program. So there's going to be parts where you can just say not applicable if it's not applicable to your crop. And up the top here, generation at which product is derived. So if it's a fixed line, then you could say F4 or F5. If it's a hybrid crop, then the answer here is at which generation do you pick your parent for test crossing? So it might be, I don't know, F3 or something like that. Do you generate genome profiles? What statistical designs and analyses do you use? So that could be alpha lattice designs with ANOVA, or it could be REML analysis or whatever. So some of this data has already been captured through some of the surveys that have gone around, like the Module 4 survey. If the last thing I want to do is duplicate the work that you are being asked to do. So if there's components here that you feel like you've already answered it in the BPAT and we'll be getting the BPATs, or if you feel like you've answered it in, let's say, the Module 4 survey, just put in Module 4 survey or whatever's easy for you. I'm not trying to make more work for you. I'm trying to get a starting position to have the conversation so that we can work together on critiquing what is currently happening, not in a critical way, but in a very positive way, to look for opportunities. And then, so this is the segregating phases. If you're a hybrid, number of new test crosses tested each year, number of new hybrid parents tested each year, number of testers used, and it's normally probably one. Just ask the question. And then product evaluation. So this is where I think it's probably relevant to all crops. So there's going to be some parts up here that are less relevant. And actually, I'm just going to lock this. Yeah.
Regarding these templates, because I'm also thinking about BPAT as well. It seems like it's probably worth making the effort to making templates that are relevant to clonal crops versus different breeding schemes, because like in BPAT, it was the same sort of thing, is you sort of have to fit it in and it's sort of not really relevant, and then it sort of leads to misunderstandings of how your program is structured. So I think the effort to adapt these templates to some general, different breeding systems is probably worth it.
Yeah, that's a great comment. I couldn't agree more, and I apologise that I haven't done this. It's for two reasons. Mostly, this had been we'd finalised this last week in Kenya, and I just hadn't had enough time. I mean, I'd worked on this early this morning to try and implement some of the things that we'd decided we'd do last week in Kenya, and look, I'd really hoped that I could have done that. You're absolutely right. So let's start with this. If there's areas that you think just don't really make sense, and you think, oh, I'm trying to squeeze a round peg into a square hole, then let's just leave that and say we'll develop a template for the clonally propagated crops, and we'll get one that works, and we'll move forward with that. But for the time being, if there are parts of this that look relevant, then it's a starting place, and we can just slot that information straight into a more appropriate form.
So I'm curious, because this is such a rich community of clonal propagated crops, do you have something of a template, or do you have something that can be built upon rather than starting at de novo?
We probably are not this well organized. I mean, we could probably be part of helping to restructure it because of our experience, but I'm not sure that we have something that's necessarily better than this. Another type of template I'm thinking about is how you cost out. The cost per plot is the other magic number.
Yeah, and that's something that we're wanting to include.
Yeah.
In this. It's possibly not here. Well, it's in one of the other tabs because we're wanting to do this for the Module 3 and 4 type activities, and so that's in the Module 4 activity, yeah.
But clonally propagated crops definitely have sort of a standard breeding structure, the types of trials, seedling nursery, clonal evaluation, preliminary yield trial. So it has clonally propagated crops have a very sort of repeatable structure and is actually simpler than most of these others. So in some ways it should be easier.
Yeah. No, I totally agree. We need to have a purpose-built template to capture that information. I mean, even if you've had some way of communicating your program in the past, I mean, that may form as some sort of template where we can then just, blank out the numbers and well, use it for that program, but then blank out the numbers to take it to others. I mean, it's a really good question. But so, I mean, we're looking for information like number of individuals, what is selection applied in this generation, or is it just a pure multiplication? Traits typically under selection. There are a number of headings here, and I mean, if we can just start to get this filled out, and fill out the important parts, that's at least something. Some of these headings are more important than others, like number of locations sampled in this generation, within site replication, number of within location environments. This may seem like a strange question. It's like the Simmet wheat program, for example. It routinely tests what it calls 5 environments, but at the same location, because it has different management, different levels of irrigation. So that's where they would have 5 environments within one location.